Hello everyone, let's wait for 5 more minutes for others to join and then we can start the session at 3:05. Is my screen visible? Okay, I think we can start today's session. So, hello everyone. I welcome you all to today's live session for this course, Digital Circuits. My name is Arpit Bal. I am a PhD scholar in Department of Electrical Engineering at IIT Bombay. I am a PMRF scholar, and this is a part of my TA duty. So, in the previous week's live session, we did a few problems on Boolean algebra. Before that, we did some problems on floating point representation and floating point arithmetic. And before that, in the first week, we did a few problems on the concepts that were covering the basics of number system. So in today's live session, we will do few few problems related to logic gates that was covered in week 4. And so before we start this session, I'll suggest everyone to grab a piece of paper and try to solve it along with me. And okay, so active learning is anyways better. So with this, we can start today's session. Okay, so yeah, so the first question that we have is, so we are given a circuit and we need to find out the function of this particular network. Okay, so we have to find out what is x in terms of a, b, c and d. Okay, I hope this question is clear. So please try to follow the approach that I am trying to do. We have already solved a similar question in the previous week's session. So okay, let me mark the nodes as 1, 2 and 3. So this node I am calling it as 1, this node I am calling it as 2, this node I am calling it as 3, this is 4, this is 5. Okay, so let us go node by node. At the first node, so we will have equation a dot b whole bar. At the second node, we will have equation c dot d whole bar. Okay. Similarly, at the third node, we will have e dot equation 1. Right. So equation 1 is this one. Yeah, Priyanka, you have a question? You can type it in the chat box and I'll look at it. Okay, so number 3 is e dot equation 1. So equation 1 is, second it will be a plus b bar. Sorry, but second is this one, right? So second, oh sorry, second should be c plus d bar. Yeah, sorry, apologies. Yeah, So yeah, that's an OR gate. So in third, it will be E dot EQ1. So EQ1 is E dot A dot B bar, right? So for the next one, that is fourth. So fourth we have E dot F. Fifth we have equation 2 dot F. Okay, so equation 2 is C plus D bar dot F. Okay, so now we need to find out the resulting equation at node X. So here we have a NOR gate, we have a 3-input NOR gate. Okay, so the output of an n-input NOR gate is basically the summation of all the inputs and the complement of that. So you can consider a NOR gate as a OR plus NOT, right? So here to get the output of X, we need to take the NOR of 3, 4 and 5. So 3 we have E dot AB bar plus 4 is E dot F plus 5 is C plus D bar dot F whole bar. That's our output. Right, now our objective is to simplify it as much as possible. So okay, so let me show you the options, and so the options will give you an idea about how much simplification we want to achieve, right? So these are the options. Okay, so now let us try to simplify it as much as possible. So the equation was AB bar E plus E dot F plus C plus D bar dot F whole bar. Okay, that will be AB bar that will be AB bar E whole bar dot E dot F whole bar dot C plus D bar dot F whole bar. So we arrived at this particular equation by using De Morgan's law. Okay, now let us try to simplify it further. So it will be AB bar whole bar plus E bar dot E bar plus F bar dot C plus D whole bar का bar plus F bar. Okay, so this will be AB plus E bar. Okay, so someone gave an answer. Okay, let's see if that answer is correct. Plus E bar plus F bar dot C plus D plus F bar is equal to, okay, there is another answer, A dot B E bar plus E bar plus A dot B dot F bar plus E bar F bar into C plus D plus F bar. Okay, so simplifying it further, what we can do is, from this equation we can take E bar common. Okay, so these terms we can take E bar common. We will be left with 1 plus AB plus F bar plus AB F bar into C plus D plus F bar. Okay, so this will be 1. So x dot 1 is x, so we can write it as E bar plus AB F bar into C plus D plus F bar. Okay, so that is option B. Okay, but okay, so it seems some people arrived at option C somehow. Okay, so can you cross check the methods that I have followed and the methods that you have used? Okay, because B is the correct answer in this case. Okay. Does anyone have any doubt in this question? Am I audible? Okay. Yeah, I hope this question is clear, right? Or does anyone have any doubt? Okay. So moving on to the next question. How one came. Okay. Okay, so in this portion, so we have the property 1 plus x. So if any of the values is 1, so the resulting equation will always be 1, right? So what I did is from these three terms, this one, and this one, I took e bar common. So if I take e bar common, then I will be left with a dot b plus 1 plus f bar. I hope that clears your doubt. Okay. So we can move to the next question. Okay, so the next question is also similar, and I would like you to give it a try first, and so you also have the options available. So give it a try, and let us see whether the options that you arrive at is correct or not. Okay, so here also you can do the node numbering. It is actually straightforward because it's a NOT gate, so you can number the nodes as per your needs. Okay, I'm just giving it a number 1 2 3 4. Okay, so in this question, 1 will be a bar, 2 will be b bar, 3 will be a bar dot b bar, 4 will be a dot b. Okay, so our output x is equal to equation 3 dot equation 4 whole bar, right? So we have equation 3 as a bar b bar dot ab, option 3. Okay, let us see. A bar b bar dot ab ka whole bar. Okay, so I'll simplify it here. So it will be, okay, so let's use De Morgan's law, a bar b bar whole bar, and this, okay, so let me put it in bracket, plus a b whole bar. Okay, I don't think we need to simplify it further. We already arrived at the answer. So the answer is option B. Is it visible to everyone? So option B is a bar dot b bar dot a dot b. No, option C cannot be correct because see the at the third point the equation that we arrive at is a bar dot b bar, and at the fourth point the equation is a dot b, and we have to take the NAND of that. So NAND is basically you take both the terms and do the overall complement. So basically option B is the correct one. Okay. Is that clear? I mean, you don't need this particular simplification, so you can ignore this. So here itself we have arrived at the result. Okay, I hope this part is clear. Does anyone have any doubt in this question? Okay, if not, then okay, we can move on to the next question. Okay, so here we have different sets of NOR gates available with us, and we need to figure out what is the final function f. So we have to represent f in terms of PQR, and we have to find a very simplified form of f. Okay, so let us do it level wise. Okay, so let's say these two are the levels. So here we have p plus q whole bar. Here we have q plus r whole bar. Here we have p plus r whole bar, and here we have q plus r whole bar. Right? So at this node we have to take NOR of this one and this one. So it will be p plus q whole bar plus q plus r whole bar ka whole bar. Okay, similarly at this node it will be p plus r whole bar plus q plus r whole bar ka whole bar. Okay, then again we have NOR. Okay, so we need to take the NOR of this input and this input. Okay, so let us write down what will be the NOR of these two inputs. So we have p plus q whole bar plus q plus r whole bar of that one plus p plus r whole bar plus q plus r whole bar and whole bar of this one. Then because we are using a NOR gate, so there will be a overall bar over the entire expression. Okay, now let us try to simplify it. So by using De Morgan's law, the first hand simplification will be p plus q whole bar plus q plus r whole bar dot p plus r whole bar plus q plus r whole bar. Okay, then we can go on simplifying it further. So what we can do is, let's write p plus q whole bar into this will be p plus r whole bar plus p plus q whole bar into q plus r whole bar plus q plus r whole bar into p plus r whole bar plus q plus r whole bar. Okay, so basically I just expanded this term. Okay, so now from these terms what we can do is we can take q plus r whole bar common. Okay, so let me write this thing first, p plus q whole bar into p plus r whole bar. Okay, so here you observe one thing interesting. If I am taking q plus r whole bar, then this particular term will be 1. Okay, so we will have 1 plus p plus r whole bar plus q plus r whole bar, and anything added with 1, the final result becomes 1. So this complete thing will be q plus r whole bar, whole bar multiplied by 1. Okay, so let's expand this thing further using De Morgan's. So we will have p bar dot q bar, and this will be p bar r bar plus this will be q bar r bar. Okay, we can take q bar r bar common again, so this term will be 1, and we are left with q bar r bar. Okay, so q bar r bar, we can write it as q bar r bar complement complement. Okay, so if we write complement twice, it means we have the original equation, but I am writing complement twice to convert this term into an addition term. Okay, so by using De Morgan's law, we will have q plus r whole bar. That is option A. Okay, so there is an answer saying option D. No, option D won't be correct because p bar term won't be there. So here itself, if I take q bar r bar common, right, so then you will be left with p bar plus 1. So p bar plus 1 will become 1, and I am left with q bar r bar as the term. Okay, so let us think, can there be an alternative to this lengthy equation? Okay, let me show you another method. Okay, just a minute. Okay, so let us try to solve it using an alternative method, so that maybe some steps we will be able to avoid. I'll write it as alternative. Okay, so here what we did is we wrote it as p plus q whole bar. So instead of writing it as p plus q whole bar, so if I use De Morgan's here itself, so it will be p bar dot q bar, right? Similarly, if I do the same thing here, it will be q bar dot r bar. This one will be p bar dot r bar. This one will be q bar dot r bar. Okay, so I can write the final result like this: p bar dot q bar plus q bar dot r bar whole bar plus p bar r bar plus q bar r bar whole bar ka whole bar, because it is a NOR. So here I can take q bar common, so I will have p bar plus r bar plus, in the next equation what I can do is I can take r bar common, I will have p bar plus q bar, and there will be this whole bar, and this equation will be, okay, let's use De Morgan's here. So we will be having q plus pr plus, if we use De Morgan's here, we will have r plus pq. Okay, whole bar. Then what I can do is I can take r common from these two terms and q common from these two terms, right? If I take q common from here, I will be having 1 here. Okay, if I take r common from these terms, I will be having 1 here. So at the end I will be left with q plus r whole bar. Okay, so here you can see we just arrived at the result with 3 steps, right? And in the previous one we had to go through all the steps, right? It was becoming a bit complicated. So here, one lesson that we need to learn is, if we are able to see a pattern beforehand, that okay, maybe I can use De Morgan's law even before that, it may simplify my problem. Okay, with only 3 steps or something I can solve it. So we have to recognize these things. So these kind of recognition, it only comes with practice. Okay, so I hope these two approaches are clear for everyone. Is this particular question clear? Does anyone have any doubt in this question? Yeah. So can you type out your doubt in the chat box itself? Okay, is this method clear for everyone? The first method that we did and the second method that we did. So here we can see that the second method is so efficient, right? We just simply so the major step was this one. Then next step was basically taking terms common, and after that we got rid of all the complement terms, and then we arrived at the solution directly. No need to use De Morgan's law multiple times. Only we used once or twice. Okay, so let's move on to the next question. Okay, so this is a straightforward question, and this is similar to the previous questions that we have solved. So can someone try this and let me know what is the answer they are arriving at? Okay, so we have one option. Okay, yeah, so everyone is correct. Basically this is a, you can see this is an AND gate. Okay, so here you don't even need to do the expression finding for each and every node, because you can see it's an AND gate, and after that there's a NOT gate. So this is basically an AND gate. Okay, this was an easy one. Okay, so moving on to the next question. So similarly, I'll request everyone to try this one out and let me know what is the answer. Okay, so you can treat it as a black box. Option C. Okay. Okay. Yeah, so option C is the correct answer. So here you can see both the inputs are tied to the same value in an AND gate. Okay, so we have A dot A bar, so this becomes A bar. So basically in this particular scenario, what is happening is NAND gate is behaving as a NOT gate, right? So whenever you are asked to implement a function where you need a complement but you are only supplied with NAND gates, what you can do is you can take the value and you can apply the same value to both the inputs, and you will arrive at the NOT gate. Similarly here we will have B bar. Okay, then we can see A bar dot B bar. So we will be having A bar dot B bar whole bar is equal to A plus B, right? Everyone mentioned it correctly, that is OR gate. So here we can see that using these gates, so using only NAND gates, we can make an OR gate. So NAND and NOR are actually called as universal gates, because we can synthesize any gate that we want from only using NAND and NORs. Okay, so yeah, let's move on to the next question. Okay, so here we have another circuit, and what we need to find out is what is the corresponding value of Y, that is this node, and Z, that is the output node. Okay, so you need to do this same thing that we are doing since the past 5 questions. So instead of using expressions like A dot B, you can directly replace the values of A is equal to 1 and B is equal to 1. Okay, so can anyone try this out? Okay, we have one answer. Let's see whether that answer is correct or not. Is there any other answer? Okay, anyone else? Okay. Okay. Yeah, so option C is correct. Y is equal to 0, Z is equal to 1. Let us see how. So A is equal to 1, B is equal to 1. So here, instead of writing the node equations, I will directly substitute the values. So if my input is 1, the output of NOT gate will be complement of that is 0. Similarly, if there is an OR gate and if one of the input is 1, okay, then I need not bother about what is the other input, right? Even though we know that A is equal to 1, but if it's an OR gate and if any one of the input is 1, then the output will be 1. Okay. Similarly, if it is an AND gate and if one of the input is 0, so the output will anyways be 0, irrespective of whatever is the other input is. Okay, so here we have 0, so Y will be 0. Okay, then again we have an OR gate and we have one input as 1. Okay, so the output will be 1. So we have Y is equal to 0 and Z is equal to 1. That is option C. So option C is correct. So these kind of patterns you need to recognize, that if you have an OR gate, okay, and if you have any of the terminals as 1, then the output will be 1, irrespective of whatever this value is. Similarly, for AND gate, if you have any value as 0, you will have the output as 0. Okay. Similarly, for NOR gate also you can remember that if you have a NOR gate, so if any of the value is 1, then the output will be 0. Okay. Similarly, you can do for NAND gate as well, that if you have a NAND gate and if any of the value is 0, then the output will be 1. Okay. So remembering these things will help you to solve bigger circuit problems easier, in a very easy manner. So okay, moving on to the next question. So is this question clear, and the method we tried used to solve this? And I hope even this thing you will remember, that if any of the one value is given for these circuits, then you can, without looking at the other input, you can tell me directly that okay, this is going to be the output, right? Okay. Okay, so the next question asks us to minimize this given circuit. Okay, so let's try to solve it node by node. So the first thing that I would like to know is, let us call it node P. Okay, so can anyone tell me what is the value at node P? Okay, so these are NOR gates. Let me write. Okay, so we have one answer, x plus y bar. No, okay, let's wait. X plus y bar is not correct. X plus y bar. Okay, so I think we have one answer, and probably you mean to say x plus y bar ka whole bar. Is that is that correct? Yeah. Okay. Yeah. So P is x plus y bar whole bar. Okay, and we have x bar here. Okay, because this is x, and after passing through the NOT gate, it becomes x bar. Fine. So let us try to simplify x plus y whole bar ka, sorry, x plus y bar ka whole bar. So that will be using De Morgan's law, we will arrive at x bar dot y. Okay, so let's call it as output, let's call it out. So out will be equals to x bar dot y plus x bar ka whole bar. It will be, if we take x bar common, we will have x bar y plus 1 whole bar. So y plus 1 will be 1, and we will be left with x bar whole bar, that is x. So the correct option is D. So this is not an inverter, but this is a buffer. Okay, so buffer will pass the value as it is. Okay, so is everyone clear with this particular question? Does anyone have any doubt? Okay, then we can move on to the next question. Okay, so this is regarding the propagation delay. So what it is asking is, so the delay times are measured between the dash percentage voltage levels of the input and output waveforms. Okay, so let's say there is a gate. Okay, let's call it we can call it any gate, let's call it gate X. Okay, and at the input of gate X, I am applying a waveform, and I get the output after some time. So what we need to say is, so between the input and output voltage levels, so between what percentage are we measuring the delays, right? So can anyone answer this question? A 50%. Yeah. So 50% is correct. So basically, this is a question related to propagation delay, and the way we measure propagation delay is, so it's by definition it is the time taken by the output to change its state with respect to the input when input changes its value. So it means, let's say the input changes from 0 to 1. After what time period, after what time will the output also change its original state from 0 to 1? So that is the propagation delay, and the way we measure it is, we take the average of the two propagation delays, right? So average of the two propagation delays, so that's basically half of T1 plus T2, that is and because we have this half term, so we have 50%. Okay, so moving on to the next question. So here also we need to do we need to evaluate the expression for y. Okay, So we have C given as 0. So here we need to use both. So in previous examples, what we have done is we are given an equation, and we try to simplify that equation further and further and represent the output in terms of the input variables, right? And in one of the question we solved that the equation was given to us, the input values were given to us, and we were asked to evaluate what will be the output value. So in this question, one of the inputs value is given to us, and we need to find out what will be the y. So let's try to do it step by step. But okay, so this is a bit straightforward. So let me call it as P, and let me call this as Q. So what is going to be the expression or the value at P? One, yeah, P is 1. And what is going to be the value at Q? So try to evaluate it step by step. First find out the value here, then find out the value here, then only find out the value here. So what I am asking is, what is this value Q? A plus B whole bar plus AB. Okay. Okay, we have a variety of answers, but okay, any other answer? Okay, so Q is, okay, let us try to solve it step by step. So here we will have A plus B whole bar, okay, and C is 0. So whatever is present here will be reflected here. So it will be A plus B whole bar. We have OR gate, this is A dot B. So OR of these two, it will be A plus B whole bar plus A dot B. Okay. Yeah. So yeah, one person gave correct answer. Okay. So next what we need to do is, so we have a 1 here. Okay. So we need to do y is equal to Q dot 1 whole bar. So Q dot 1 is anyways Q, so we just need to write what is Q bar. So Q bar is A plus B whole bar plus AB whole bar. Okay. So do we have this option available? Okay, we don't have this option available, so we need to simplify it further. Let's try to simplify it. Okay, so first stage of simplification will be A plus B whole bar ka bar plus dot AB whole bar. Okay, so this will be A bar plus, this will be A plus B into A bar plus B bar. That will be equal to A dot A bar plus A dot B bar plus B A bar plus B B bar. Okay. And using the property that if x dot x bar is present, then it is going to be 0. So similarly this will be 0 and this will be 0. Then we are left with AB bar plus BA bar. Okay, that is option A. Okay, so I'll pause here for 1 minute, and so if anyone has any doubt in this particular question, how we solved this, so they can let me know. Okay, so to solve these type of questions, what you need to do is you need to have a step-by-step approach. So first try to replace, so whatever information is given in the question, so try to utilize that. So if the variable value is given to us, let's say c is equal to 0, so first substitute all the nodes which has a value. So you put c is equal to 0 here, so you will get 1 here. Similarly, you put 0 here. Okay, and we know that if any one input of OR is 0, then the output will be equal to the other input. Okay, so that's what I did, so that gets reflected here. Okay, then after putting all the values that are mentioned to us, what we need to do is we have to figure out what is the equation at each and every node. That's what we did. We started from the innermost node, we found out a plus b whole bar, then we figured out a plus b whole bar, means after the OR, then we figured out the value at q, then we arrived at the value at y, and then we tried to solve it further, okay, till this point. I hope this question is clear. Okay, so okay, so we can move on to the next question. Okay, so here the question is, the gate ideally suited for a bit comparison is which gate? So which gate will you give preference to if you have to perform a bit comparison? Any answers? Option A, option B. Is there any other answers? Okay, so I'll wait for 1 more minute for you to come up with the answers. Okay, can anyone tell me why it can't be option B? So yeah, the correct answer is option A for sure, but what I want you to do is reason out why it can't be option B or option C or option D. Okay, let me give out the reasoning. Let us assume that it is the correct okay, so the correct answer is option A, but let us assume that I am choosing B as the correct answer. Okay, and let me prove that it's the wrong answer. So let us say I take A is equal to 1 and B is equal to 1. So here basically both the inputs are same. So what I will get the output of OR gate is 1. Okay, let us assume that A is 0, B is 1. Okay, so these are different, right? But still the output of OR gate will be 1. So OR gate is unable to distinguish whether the inputs that are given to it, whether it is same or whether it is different, right? The same thing is going to happen for a NAND gate as well. You can verify taking examples on your own. And similarly, even NOR gate is going to do the same thing. So if any gate is unable to distinguish whether the inputs that you are giving to it is same or different, then it cannot be used for bit comparison, right? But when we take XNOR, yeah, so there's a doubt. Yeah, you can type it on the chat box. Okay, so then what makes XNOR so special that we can use it for a bit comparison? So let us say I take A and B as something same, 0 0. So XNOR output will say 1. It means that they are same. If I take dissimilar bits, 0 and 1, XNOR output will be 0. So what we can say from this is XNOR is able to identify the similar and dissimilar bit patterns. If you give similar bit pattern 1 1, XNOR is going to say that it is 1, that it is matching. If it is 1 0, it is going to give you 0. Okay, so similarly we can also use XOR as well, because XOR is also going to distinguish, right? XOR will give 0 for all 0 or all 1, and it is going to give 1 for 0 1 and 1 0, right? So these two gates, XNOR and XOR, can be used for bit comparison. Okay, but yeah, usually XNOR is preferred, because if it is similar, then it is going to give you 1. So because similarity kind of resembles a positive something, so that's why XNOR is preferable. And yeah, so the correct answer is option A. So when you try to solve these questions, so not only you try to arrive at the correct answer, but you should be able to reason why this answer is correct and why the other answers are not correct. I hope this part is clear. Is there any doubt in this explanation or in the answer? Does anyone have any doubt here? Okay, if not, then we can proceed with the next question. Okay, so here we are given a input to a logic gate. Okay, so the logic gate is given as XOR. Here we have A and here we have B. We have to figure out what is Y. Okay, so can anyone try to solve this? And options. Okay, let me wait for others as well, if we somehow arrive at a different answer, so that okay. Okay, is there anyone who says that it is going to be option D? Yeah, it won't be option D anyways. So yeah, so the correct answer is option C, 0 1 1 0. And how we arrive at that point is 1 0 1 0. You do the XOR of this. So XOR means if it is dissimilar, if the bits are dissimilar, you give a 1. Okay, so we can see these two bits are dissimilar, so it will be 1, and the rest is 0. So we arrive at this point. Okay, moving on to the next question. Okay, so here we are given an expression and we need to use only NAND gates to implement this particular function. Okay, so can anyone try? And yeah, the NAND gates that we are going to use, so the constraint is we need to use the minimum possible number of NAND gates, right? So okay, so here, okay, let me tell you one more assumption. So the assumption is the variables A, B, C are already available to you. Okay, and you have to implement this function. Can someone try to simplify this? Okay, we have one simplification. Is there anyone else who wants to simplify it? Okay, so yeah, let us try to simplify it. So here if I take a common, then it will be 1 plus b bar plus b bar c. Okay, so this term becomes 1 and we are left with 1 a. So as I mentioned earlier that these inputs are already available to you, so there is no need of using any NAND gate at all to implement this function. You directly just give it to the output. You have the output ports here, you just give it to the output. Okay, so the answer is A. Okay, so moving on to the next question. So this is related to the implementation of CMOS inverter. Okay, so the question here is, so you have the CMOS inverter available, and from where do you need to measure the output voltage? So what can be the answer to this question? Okay, we have one option here. Let's wait for others' answers. Okay, I'll wait for 1 minute for any answer. Okay, we have another answer. Drain of NMOS transistor and ground. Okay, any other answer? Let me draw the CMOS inverter. Okay, so can anyone tell me where is the input? So I'm marking this as X and Y. So which is the input in this case? Okay, basically what I did is we have this structure, and this is what the magnified view looks like. Okay, yeah, so X is the input, and so subsequently Y is the output, right? This is the PMOS, this is the NMOS. Okay, so let me mark these terminals. Okay, okay, so we have almost all the options covered in the chat box. So someone said option B, someone mentioned option A, someone mentioned option C. Is there anyone who wants to mention option D as well? Okay, yeah, so okay, so the arrows, they actually represent the source terminals. Okay, so this is the NMOS, this arrow represents the source terminal which is connected to the ground. This arrow represents the PMOS source terminal which is connected to VDD. Okay, and we are taking the output Y. So now can anyone answer it? Okay, so basically we are taking the output here. Yeah, option A is the correct answer, that we are taking the output from the drain of NMOS transistor and ground, right? Can there be another answer possible here? So those options are not mentioned here. So from the given options, option A is correct. So can anyone suggest me another answer to this question? So okay, I'll tell you that there are two more answers that are possible. Looking at the pattern in option C, can anyone suggest me one more answer? Yeah, so we have one more answer here, that BS source and drain can exchange, correct. So here you can see this is the drain of NMOS, as well as it is the drain of PMOS. So in option B it is mentioned that source of PMOS. So instead of source we can say that drain of PMOS transistor and ground. So that is also the correct answer. Okay, so can there be any other correct answer? Okay, let me give you a hint. Let's say this is my inverter. From here to here it is VDD. Here to here it is Y. Can anyone think of any other possible answer to this question? Okay, anyways, actually these two are the correct answers. So you can say that it is either drain of NMOS transistor or the point where drain of NMOS transistor and drain of PMOS transistors intersect to the ground. Okay, that can be another answer. So this was the last question that we had. Okay, does anyone have any doubt in any of the questions? Okay, let me summarize what we did today. So most of the problems that we solved today were related to simplification of circuits, so simplification of logic gates and finding out the expression from them. And let's say we have a collection of logic gates that is given to us and a set of inputs. So in today's live session, what we learned is how to solve those intermediate gates expression. And please explain last question. Okay, so we'll go to the last question. Yeah, so you are referring to option B, right? So instead of B, if it is written as drain of PMOS transistor and ground, that could have been a correct answer as well. Okay. Yeah, so for the first question, what we did is we tried to figure out what will be the intermediate nodes equations. Okay, so we started giving nodes different names, like I use numerals, but you can use anything. So you can call it A, B, C, D, provided you do not get confused with the inputs as well as the node names. So what I did is I tried to figure out what is the respective equations at those particular nodes. Then what I did is, after resolving one level, I went to the next level and figured out what is the equation for those nodes. Okay, then we proceeded to the last level and we figure out what is the equation for the remaining for the last node, and we arrive at this particular node. Then what we do is we try to simplify this complete equation. Okay, so here for simplification purpose we have used De Morgan's law multiple times. Okay, so yeah, so we have used De Morgan's law multiple times. First time we used De Morgan's law, we have arrived at this equation. Then again we tried to use De Morgan's law, we arrived at this equation. Then what we do is we again use De Morgan's law. In the next step, what we do is we try to expand these two terms. Okay, and after expansion what we do is we take E bar as common from this particular term 1, term 2 and term 3. Okay, so after taking E bar common from these three terms, what we end up with is 1 plus AB plus F bar, and using this equation 1 plus x is equal to 1. So what we do is this term vanishes as 1 and x dot 1 is always x. So using that, we have this simplified form as E bar plus AB F bar into C plus D plus F bar. Similarly, the next question also we tried to solve using the previous methods that we have learned. We try to figure out what is 1, what is 2, what is, then after figuring out 1 and 2, figure out 3, then we figure out 4, and ultimately we figure out x. Okay, and we saw that no further simplification was required, and this was already an option which was given here, so option B was the correct answer. For question 3, we solved that, we observed that it can be solved using two methods. One, if we directly go on substituting the main values, like for NOR, we know the expression that it is going to be the NOT of the input summation. So I do P plus Q whole bar at this node. Same thing I do at this node, this node, this node, and all the nodes. And then we try to simplify the complete expression. But we observed that it becomes a bit lengthy and a bit complicated if we try to do by this method. So we thought, was there any other alternative method possible? So yes, it was possible. What we did is, instead of writing P plus Q whole bar, we used De Morgan's law here itself and tried to write it in the form of P bar Q bar. Okay. Then what happens is, then it got simplified as Q bar into P bar plus R bar by using De Morgan's theorem once. After that, what we did, we took Q common from the terms which was containing Q and R common from the terms which was containing R, and we arrive at this equation in at max 3 steps, and it's relatively simpler and easier in comparison to the previous method that we used. Okay, the next question was related to identifying the gates. Suppose it was a black box that was given to you, you had to figure out which gate it was, and almost everyone gave correct answer that it is NAND gate. Okay, then in the next question what we observed is, how can like a combination of NAND gates be used to realize several gates. So here NAND gate was used to realize a NOT gate, and in this complete box NAND gate was used to realize an OR gate. Okay, so NAND gates are called as universal gates because it can be used to synthesize any gate from using a bunch of NAND gates or NOR gates. Okay. In the next question, what we did is, we were given values for A and B, and we were supposed to figure out what is the node Y and Z. So the first thing that we did is, we substituted wherever we have A as 1 and wherever we have B as 1, that is the assigned value, and we tried to figure out what is going to be the values at the corresponding nodes. And then we discussed an important property of gates, like if it is an OR gate and if any one of the input of the OR is a 1, then the output is going to be 1 irrespective of the second input. Okay, whether the second input is a 1 or 0, we need not bother about it. Similarly, for AND gate, if one of the input is 0, then the output is going to be 0. Okay, similarly for the NOR gate, if one of the input is 1, then the output is going to be 0 irrespective of the other input. Similarly for the NAND gate as well, if one of the input is 0, the output is going to be 1 irrespective of the other input. The next thing that we did is, we had to minimize the circuit that is available with us. Okay, so I'll tell you one practical application of such kind of minimization methods. Let us say you are designing a very huge complicated systems which is consisting of a number of logic gates. Okay, and you observe such a pattern arriving. Okay, and you observe that you don't need these many gates. Instead, what you can do is, you can replace it with a buffer, or you can just connect a wire from X to the output. Okay, so it can lead to using minimum number of logic gates as well as saving power. So when you actually design any digital system, so these kind of things will be helpful, because you can observe all these gates are not required to realize this logic, so they become redundant but unnecessarily consume area and power. Okay, so this is one practical application of this minimization method. The next thing is, we discussed about the propagation delay, that is measured between the input and outputs 50% level. Okay, then what we did is, we are given a circuit and we need to figure out the logic expression for y. So whatever value, initial value was given for the input, we substitute that value. Okay, then we tried to solve the remaining set of equations that are available with us, output, so the intermediate expressions, like we figured out the expression here, 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 and then here. Okay, then whatever expression we got here, we tried to simplify it further and we arrive at this result. Okay, then in question 10, what we did is, we figured out what is the gate that is ideally suited for bit comparison. And we also, here we learnt one more thing, that so while solving these kind of questions, we need to keep in mind that if we figure out the correct option, we also should be able to reason out why the other options are not correct. Okay, so here we did the same thing for OR, and similarly it can be shown for NAND and NOR as well. You can come up with expressions and you can show that if A and B are opposite, or if A and B are similar, so if the output is not going to be different, then that gate is not suitable for bit comparison. And we also showed that XNOR and XOR both are suitable for bit comparison if needed. Then we were given a logic gate XOR, and we were supposed to find out the output of the given input pattern. A is equal to 1100, B is equal to 1010. We just simply need to take the XOR of the bits, and that's what we did here. And for XOR, the thing is, if you have dissimilar inputs, then the output is going to be 1, else it is 0. So that's what I used, and we have the answer here. Then we were given a function and we were supposed to implement it using minimum number of NAND gates. So this is again a minimization problem, that if you are given a big expression, so let us say if this expression is given, and what you do is, okay, you connect a wire directly for A, then you connect a AND gate, NOT gate. Okay, let us assume you have a 3 input OR gate available with you, and for this one you have a, okay, we already have a B bar, we have A, let's say we have another C. Okay, so this huge thing, it can be replaced with only a wire or a buffer which connects A to the output, right? So I hope you are able to understand the importance of this minimization methods that we are using here. Okay, so because the function reduces to A, so we don't need any NAND gate. So the next question was related to CMOS inverter. Okay, so yeah, I think someone was asking about this answer, so you can also mention it. Let us say you are taking VDD as a reference, so you can also mention it as VDD minus Y. So I could have also said that if you are taking the output between the source of PMOS, or else if I say that you are taking the output between the drain, between the supply and the drain of PMOS, then also the answer would have been correct, because we are just changing the reference, right? But anyways, so this question, what we were supposed to figure out is which of the following options are correct. Let's say we are given a CMOS and we need to figure out where we have to take the output from. Okay, so the input is applied at the gates of the PMOS and NMOS. So basically they are connected, and the drains are shorted. So PMOS drain is shorted to NMOS drain, and in NMOS the source is connected to ground. In PMOS the source is connected to VDD. Okay, and so the output is taken across this, right? So that brings us to the end of today's session. So I'll stay here for some time. If anyone has any doubt in any question, they can let me know. And these recordings will be available after this session is over in my YouTube channel. So I think the sheet, the Excel sheet containing the links for the YouTube channel and these lecture slides are available with you. If not, you can also check in NPTEL TA Arpit Bal. So there this complete recording will be available along with the other recordings of the previous week's live sessions. And what I will suggest you is to practice these questions without looking at the solutions. You can directly look at the questions and try solving them on your own. Like in today's session, there were at some questions I observed that someone was giving a wrong answer. So for those questions, what you can do is you can see where you went wrong, because the correct answer is not as important as the method that you use, and where you went wrong will be okay. A link of my YouTube channel. Okay, just give me a moment. I'll share the link. Yeah, I think I have shared the link. So this is the link to the YouTube channel, and today's lecture will be uploaded after 5:30, so you can check there. So it also contains the previous week's lectures as well, the live tutorial sessions whatever we had so far, so it is there. Yeah, so does anyone have any doubt in any of the questions that we solved today? Okay, so I hope these sessions are helping you in clearing your concepts related to your lecture sessions, and it is also helping you in solving your assignment problems. Okay, so yeah, so I think so we can wrap up this session, and if anyone has any doubt, so I'm still here, so you can let me know in the chat box. Or if after going through the lecture videos again, if you come up with any doubt, you can post your doubts and queries in the NPTEL forum. You have a ask a question section where you can post your doubts, whatever you have. So yeah, okay, else we can wrap up today's session. Okay, I'll still be here. If anyone has any query, they can let me know. Fine. Okay. Thanks everyone for joining.